sigmas are the big deal. Sigma takes this transversal system and two values k and j, and we can create a symbol. So why don't we do that? Let's defun sigma symbol with k and j, and we'll do Alexandria, I think, has something like this. Alexandria format symbol. Yep. So Alexandria format symbol within the keyword package. Our control is going to be sigma d. Looks like a good symbol to me. KJ. So if we do sigma symbol for like 5 and 2, for example, we get this wacky looking symbol right there. I'm wondering here if you're wondering what sigma is. So a sigma is a permutation, any permutation that maps the value k to the value j. So as long as, if we have a permutation of numbers between 1 to 10, for example, and if the value of the 8th value maps to 4, then that would be a sigma 8, 4, written like this. Where is it? 8 and 4. So as long as we map this k right here to j, then it's considered a sigma. And obviously there are a big number of those. I mean, we can have lots and lots of permutations that map 8 to 4, but that's the only property that it needs to satisfy. So we have sigma symbol, and the idea is that we're going to store our sigmas in our straight line program assignments. So I am going to, within generate perm group, make a table for that. So in fact, what I'm going to start by doing is making a global def var. I'm going to try to use wizardry, aka dynamic variables here. So def var assignments as just that. It's just this empty, lonely variable. So we assign assignments here to, yeah, sure. Let me write this line, then I'll go over it. So make instance SLP assignments. Is that what I called it? Yep. Okay, so as a recap of what I'm trying to do, when I generate a perm group, let me actually do this. So we have perm examples, make Rubik 3x3, and let's choose a random element, a random group element. So I make this group, and this is a random Rubik's cube right here. The idea is I want to take this random Rubik's cube and be able to generate the turns that make that random element. That's equivalent to solving the cube. I want to be able to solve this Rubik's cube. Now, the way I'm approaching this will not produce an efficient solution at all. In fact, the solution might be hundreds or even thousands of elements long, which is not efficient. But the point is that we can take any group at all, like a Rubik's cube, like an arbitrary permutation group, and given some random element of it, I want to be able to decompose it into the so-called generators. Here on the cube, the generators are quarter twists of each side. So, but that's hard, you know, given this is a random Rubik's cube, but all we do is have a list of numbers representing the stickers of the cube. We do have an ability to decompose this into sigmas, however. And I can get that by computing something called the transversal decomposition. So if I do, if I compute the transversal decomposition of that within our, did I define cube? Yes. So if I do transversal decomposition of the permutation, let's say the double star means this right here, within the cube group, we get all of these things. So it's saying that, yeah, 100 move T-perm, that would be funny, but we can do it. We'll make a new T-perm. So anyway, this transversal decomposition, what this is doing is it takes an element of the cube group, like this one, and it breaks it up into these constituent sigmas. Let me actually clean this up a little bit by removing the identities. T so 1, 2, 3. Okay, so what this is saying is that this randomly generated group element is composed of these weird things. Each of these things is like a coordinate pair. These coordinate pairs actually represent sigma. So, for example, that 18.7, if I can type this, represents this sigma right here. So if we find the value of all these sigmas right here, which we know the value of each sigma, we can look them up in a table basically. We can find what this permutation right here is as composed by sigmas. The big problem, however, is that sigmas, we don't know how to represent sigmas as their base terms on a cube. We don't know how to do that. So what I'd like to try to do then is figure out what all these sigmas represent. So if we can decompose any random element right here into sigmas, and we can decompose sigmas into the normal generators, then that means transitively that we can decompose this thing right here into generators. So that's the general approach I'm taking. And the way I'm doing that is when I construct the sigmas, for example, a sigma is set right here. When I construct the sigmas, what I'm going to do is, it's this really horrible, that's actually exactly right. The sigmas are going to be solving one sticker of the Rubik's Cube at a time. Now it'll turn out, because of Rubik's Cubes, if you solve, 2 stickers right here, the third one's automatically going to be solved. But that's what's happening, is it's going through, it's the dumbest thing. It goes through one sticker at a time and solves it and puts it into place. In a very efficient way. We need to figure out what moves we can do with that. It is super, 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 super naive. But again, it works for any puzzle possible, anything possible, and it's a completely deterministic procedure. Yeah, all this code is for something dumb, that's true, but then we will be surprised in the coming months what actually turns out from this code. So let's go back to our assignment. So what we're doing is we're making an SLP assignments thing. We're going to make this SSA sort of deal. We also need to make a free group that goes along with this. So free group, I'm just going to call it FG. Make instance free group with num elements as the length of the generators. That would make evaluating SLPs very, very fast if you could JIT compile them. Okay, so let's compile this. What's the warning? FG. Okay, that's fine. So what I want to do now, I'm going to make another value called current generator. Current free group generator. This is just, all this is going to contain is whether we're, when we build our Rubik's Cube up, we start by telling it about the move F, and then we tell it about the move, or I should say F right here. Then we tell it about the move B, and then we tell about the move U. We're telling about one move at a time, and so basically this variable right here is going to contain that move that we're telling it about at that point. So current free group generator is right here. Uh-oh. I have no idea what I just did. I have no idea what that button just did. Where'd my little chat go? Where is it? Okay, there we go. Control D, just cancel it. Okay, good, we're back normal. I got really scared that I accidentally closed everything just now. That would have been very, very bad. So the generators are going to be, so we're going to start with let current free group generator, did I not compile that? Generator, it's going to be 0 at the start, and then we're going to increment it each time. So incf current free group generator. That should work, I think. Alright, so each time we're incrementing the generator to be something bigger. The first generator, I mean, it starts as 0, but before we actually add the generator, it's going to be 1 because we increment it. Then when we add the next generator, it's going to be 2, and then 3, and so on. It does. So it does, I don't know why I was typing, but it doesn't need to be global. The reason I made it global is because I'm not going to pass this value to this function yet. Later on, I will probably want to make it not global, but it's easier right now, instead of trying to modify 4 different functions to take a new argument, I'm just going to make it global at the start, and then I'll change it up later. So, let's see here. So how do we go about this? So it's gonna start by calling add generator, and current free group generator is going to have a value attached to that. And we need to remember every single thing that we encounter. Everything, no exceptions. So if we look, for example, at this perm compose, this product right here, we need to remember how this product was generated. Well, the product is generated by way of these these tau values, and so let's see. So what we want the k and j values. We need the sigma. That's what I'm trying to say. We need the sigma. So for what is it? Using hash key j seems reasonable to me. We do the following. Let's just close that off, and once reading done this to be even bigger. So our sigma is now with sigma